So now I'm going to introduce this notion of a Fourier transform for locally compact abelian groups. So if you recall, in the classical harmonic analysis, if you have, say, f in the, say, a 2-pi periodic functions, then the Fourier transform is given by this integral. So for each integer, you integrate your f of x against the e to the, say, negative I n x dx, and that's basically give you the Fourier transform. So a lot of time the function, the property of the function corresponds to these Fourier coefficients. You can treat your Fourier coefficient as basically a this f hat is a function from the set of integers to the complex, let's say. All right. So that kind of idea actually also translates in the case of a locally compact abelian group. So now we already see that this e to the negative I n x, that's basically a character. So we just introduced it in the last week. And so we basically now just replace this this e to the I n x by the character. All right. So basically we define the Fourier transform as a function on the dual group. All right. So here's the definition. So suppose I have a function, let's say f inside the L1 of G, all right? Then I define the Fourier transform. So the Fourier transform of this function f, that's denoted by this notion. Let's use f hat. So this is a function that's given from the start from the dual group to the complex, defined by the formula f hat. If I give you some character, let's say phi, then what I do is I integrate the function value against the conjugate of the character, okay, and dx. And as you can see, in the case of when G is just the unit circle, then the dual group is the set of integers, and the characters are essentially just this e to the negative I n x, or e to the I n x, and you do the conjugate there, all right? So sometimes you can also write this as there's some other way of writing it. For example, because phi is a character, this is also fx phi of x inverse dx. Okay, so they're essentially the same thing. And the reason this is integrable is just really easy to check. Your function f is in L1, so you multiply something in L infinity, so you get another function in L1. All right, so this is certainly well defined. All right, so now I just want to point out one thing. This map where you map f to this f hat is actually a star homomorphism. So your L1 has a star Banach algebra structure, so it has a convolution, an involution, and your f hat, you can treat it as some function in the g hat, and it turns out you can make it into the C0 of g hat. And that's going to, this map is going to respect your involution and convolution. All right, so let me just write down the proposition. So this map, mapping from f to this f hat, basically is Fourier transform. Sometimes you use the notation f. Okay, I rarely use that, but if you follow Folland's book, I think that's the notation in his book. So this map, it maps f inside L1 of G, that maps into the C0 of G hat, all right? And this is actually a norm decreasing. And it's also because L1, again, has the Banach star algebra structure. The C0 of G hat also have a multiplication, the usual pointwise multiplication, and taking the conjugate, basically the inverse, the involution, all right? So with that, so this is actually, and it's actually a star homomorphism. Okay, so it's a star homomorphism, and by star homomorphism, I should explain a little bit more. So if I take the convolution of two things and I take their Fourier transform, then this equals to the product of their Fourier transform. So here everything is abelian, so because our group is abelian, so it doesn't really matter the sequence. And if you do the involution of this f, and you do the Fourier transform of that, then what you have is something like the fx inverse All right. And if you do the involution of f, so we use the notation f check to denote its involution. So let me just maybe write it down. Recall this is just fx inverse. All right, then you can also talk about the Fourier transform of the involution. So let's do the f check involution. This is actually just the involution on the C0 of G, which is just taking the conjugate. So it's you take the Fourier transform first, and then you do the conjugation. All right, so this is what I mean by the star homomorphism. And moreover, the range of this map, so moreover, the range, let's just use this notation f of L1 of G. That's basically all the Fourier transform that's going to be dense inside C0 of G, all right, or G hat actually. All right, so the proof of this is actually just fairly simple. If you study the operator and Banach algebra theory, then this is essentially the result of Galfand transform. So I'll just say this is essentially proving the Galfand transform or the Galfand theorem. Okay, so let's just say Galfand transform. So in general, if you have a Banach algebra, then your Galfand transform basically maps your algebra into the C0 of its spectrum. And this map is norm decreasing. And when certain thing happens, it's also star homomorphism. And the range is dense in when you have some nice properties, of course. All right, so so because it's a result of the Galfand transform, I'm not going to talk too much about it. You're going to learn it in maybe A10 when you take the Banach algebra course. So I'll just briefly outline some of the more technical part. All right, so first of all, if you do the f hat of a character phi, okay, so if you consider y is norm decreasing, is that this is kind of quite standard. So you do the integral of the phi bar dx, all right, do the integrate against the Harmonic measure. And again, you do this standard trick, the absolute value of the integral is less than or equal to the integral of the absolute value. But because your character always have norm 1, so it's less than or equals to the integral of the absolute value of f, which is the 1 norm, right? So the f hat, the sup norm of f hat, so is going to be, well, the supremum over f hat of these phi, so that's going to be less than or equals to 1 norm, right? So that's finished the norm decreasing part. And y is a homomorphism, so let's consider if we conjugate two things, f and g, and I want to evaluate at some character phi, then let's just write this out. This is the integral of f and g convolute with evaluate at x, and you evaluate against your character phi bar of x, and then you do the dx, the left hand measure. All right. Let's expand the convolution again. So this is f of x y inverse g of y. That's your convolution evaluated at x, and then dy. And then you do phi bar of x dx. All right. And because your x and y, they're just hard measures, so let's just do some translation. So if I, first of all, switch the integral, so let's do the gy out, and then let's integrate the x first. So I have xy inverse phi, let's just say phi x bar dx, and then you have a dy. Then the standard trick, you can move your x, you can right translate it by a y, so the y inverse get cancelled. So this becomes integral of gy, integral of f of x. Now the x translate by y, you cancel out the y inverse in there. So you have a xy in the phi bar, okay, dx dy. And then now you can write this is because your phi, remember phi is a character, so phi is in the dual group. So phi xy is phi x phi y. So you can break it into two parts. You break the phi y, give it outside to the gy, and then you do the other thing, the fx phi bar of x dx. Okay, there you can basically break this double integral into the product of these two integral, and you realize this is essentially just g hat times the f hat evaluated phi. Okay, in the C0 of the g hat, the product is just pointwise multiplication. So basically now you show the convolution of the Fourier transform of the convolution is the product of the Fourier transform. And you can check the involution part as well. So let's do the f check. If you do the Fourier transform of that, okay, so the notation looks really ugly, but it's just nothing more than you integrate your function, let's say f check of x, and then you do the phi x bar dx. And let's just plug in the formula. The f check of x is just the fx inverse, the whole thing conjugate, and then you have a phi x conjugate dx. So there are a bunch of conjugates, so let's just do everything conjugate. So you can ignore the conjugate inside. You have fx inverse phi of x dx. All right, and now you remember your group is abelian, so the modular function is going to be equal to 1. So when the modular function is 1, it allows you to switch your integral from x to x inverse, okay, without any cost. All right, so let's just make x into the x inverse. So let's replace all the x by x inverse and x inverse by x. So we have that dx, the whole thing conjugate again. And whatever is in there is just the Fourier transform of f evaluated at phi taking the conjugate, all right? So let's finish the last bit of the proof. All right, and also, okay, so we now need to show that it's going to be dense range. Well, this is just really follows from the Galfand theory. I should also mention that the f hat in the C0 is also basically follows from the Galfand theory. I'm not going to prove that. And the range of this f of L1 of G, from the Galfand theory, we know that actually separate points. And because it's separate points and this range is, this L1 is certainly a Banach algebra. So when you do the star homomorphism, the image is still an algebra. So you can do the Stone-Weierstrass, okay? So it's going to be dense inside the C0 of the G hat, okay? So this is simply from the Stone-Weierstrass theorem. I just want to give you another fact from the Galfand theory. I'm not going to prove this fact. So in fact, if you want to know what is the f hat, the infinity norm, well, this is, in most cases, it's not going to be the L1 norm, but you can actually use the following formula, which is very nice. So it's in fact the limit of the following. So you can compute the convolution of your f against itself, say n times, and then you raise it to the n times, so you raise it to the 1 over nth power, and you let n goes to infinity. Okay, so it turns out the infinity norm is going to be equals to this limit. Okay, so of course, on the right-hand side, when you have an L1 function, you convolute it n times, you still have an L1 function, so you take its one norm on the right-hand side. So this formula sometimes is called the spectral radius formula. I'm not going to cover this in this course, but it's a really important formula when you talk about the Galfand theory.